Okay, so let's talk about the meat tenderization and continue to talk about that. We do a brief review. The topic is meat tenderization. So let's do a brief review what we talked already. So let's say we had in the middle we have like A band. Okay, the A band, right in the middle we have an M line. That's a muscle structure. Then on the side we have a I band. Okay, I band on the side. At the side of the I band, in the middle we have another line, which is we call the Z line. And the distance between two Z lines, we call its a single unit of a muscle microstructure called the sarcomere. And then we talk about in the sarcomere, there is a very important structure right in the middle, which is a little bit thick structure with some of the thing like we call it like a sprouts on the top. So this is we call thick filament, and those dots we give them a name called myosin. And at the same time, we're using another color at the same time, we also have some thin filament, like this, like that. And these thin filaments could be connected with thick filament. And this is, we call it actin. And that's thin filament. And we learned in the other classes, there is a cross link between myosin and actin. So we call this is actin myosin cross link or cross bridge. And that is very important structure for muscle contraction and relaxing. And at the same time, we also talk about surrounded the Z line, there is a huge protein, huge group of protein. And that could be like nebulin, like titin, like desmin, and on, etc. So we say. Okay, so this is a muscle sarcomere. And then we mention about a very important curve here. Is after the carcass has been harvested, they're going to go through a process which is called RM, rigor mortis, the toughness of the muscle. The rigor mortis have a onset time, then we also have a rigor mortis time, and then we have a resolution time. Now at the same time, we can draw another figure kind of very interesting. We can spread them into different phases, this is called onset. This is a rigor mortis time, and the last one is a resolution time. And what you can see, the rigor mortis, the curve looks like this. But at the same time, you will see other curve looks like that, one. Another curve looks like similar. And another curve is also very similar, looks like this. These three curves indicate the ATP. We have a pH, And we also talk about the glycogen amount. So related to the muscle tenderness, we are talking about actin myosin cross-link here. We try to break down. And we also talk about the protein surrounding the Z line. We try to break down. And in here, this is related to a lot of the factors, especially like the ATP present or not present. And all these proteins surrounding the Z line going through proteolytic process. And they rely on a calcium amount, because the calcium amount will regulate the internal enzyme in the skeletal muscle, which is called calpain. And we mentioned about the inhibitor, which is called calprastati. And some of the species, some of the breed have a high amount of that, could inhibit the calpain's activity. So this is where we end up like last time. Then we're going to continue to talk about. Now, during the history of the meat science, and the meat science is also an applied science. So people get the meat, then testing quality or even safety. Then what they find is there's a phenomenon which is a problem called cold shortening. So what happened is, this is in 1960s in New Zealand. And New Zealand is because it's an Agriculture Consumer Integrated Association, they receive a complaint about very tough lamb. Well, of course, those could come from a large industry or come from small producers. Then we're going to talk about what is a cold shortening. So cold shortening, which means you are chilling carcass below 50 degrees Celsius. At the same time, rigor mortis not initiated, not started, and ATP still present. And this will cause calcium dramatically release from sarcolemma reticulum, SR. So what happened is significant shrink or shortening of muscle. You can say this sarcomere is completely shrink. How severe it is? Around 80%. And also will give you a very tough muscle. So that's a problem. Okay, now, how are we going to prevent it? How are we going to prevent that issue? There is a several ways we can do. Number one is slow cutting. Absolutely not before rigor mortis complete. This is very important for small producer, because when they do the harvesting, after harvesting, they want to be sliced immediately, then do the packaging, then do the chilling, because they want to go out of their factory, go to the markets. The second thing, so if you notice that, most of the time what they do, let's say we have a carcass, we are always handing them upside down. So we call it a tender stretch. And we have to do is hanging arch bone, not a childless tender. So which means you are upside down. Number 3, lots of the company already start to using and used wider right now is applying electronic stimulation. So when they do the electronic stimulation, they could contribute to 3 important actions. Number 1 is physical damaging. So like, let's say you have a muscles here and the active myosin. We can using a physical methods to break it down. Because they could happen is a severe muscle contraction. And we are doing electronic stimulation, let's call it physical damage. The second thing, using electronic stimulation could accelerate the calcium release. The calcium release from the sarcolemma reticulum could be activated calpain and then will be speeding up the proteolytic process. So these proteins could be hydrolyzed. Okay, so certainly loosen them, the bonding between the Z line. The last one, we can accelerate the glycolysis process. And the accelerated glycolysis process, this is be tricky, have to be reach appropriate pH. Appropriate pH value, because this is related to the water holding capacity. Okay, so that's the reason we are doing these right now. But cold shortening is one of the issues during the tenderization process is happened in the history. And you can see some of the pictures. A beef looks like this large. Cold shortening is only like one section. It's only like 20% of that. Looks like majority of the beef has been disappeared. Well, that's cold shortening. Now we also want to mention several things is that happened on the typically in the pork. There is an issue and very common called the PSE pork. So we can talk about this one. So PSE pork is an issue related to the quality of the pork. So number 1, what is a PSE stands for? That is a pale, soft, and exudative. Exudative. Let me see how to spell it. Exudative. Which means some of the moisture will be extracted out. So pale, soft, exudative pork. So what that happens? The story is that for the pork, which means swine or pig, basically is pig or hog, which we just say like a hog. Then after post-mortem, about 45 minutes, the pH ideally should be around 6.6 to 6.8. So remember this guy right here. pH, water holding capacity. The curve looks like this. Okay, after you're doing started from here, around like 7, you should be only like 6.6. Now what happened? The pH for PSE epoch dramatically or rapidly decreased to less than 6.0. Sometimes all of a sudden goes 6.2, or then goes to 5.8, all of a sudden. What this means, water holding capacity will be low. Once the pH below 6.8, it's very close to the IP point, or we say PI points, isoelectric point. At that moment, the water holding capacity is lowest. But at the same time, the temperature is high, still around 37 degrees Celsius. So pH dramatically decreased to less than 6.8. The temperature is still high, around 37. These two things alone will cause the denaturation of contrail muscle protein. Therefore, will cause PSE. Now, what are the factors will cause? The reason will cause PSE. There are two reasons. Number one is stress. Stress, there are two major stress. One is heat. Another one is transport. So there are lots of research about transport and heat stress related to the animal welfare. Lots of the research do that back in like 20, 30 years ago in China, because China is a big country for to create amount of the pork instead of have the beef. This is one thing. Second is some genotype. We have to avoid it. There are some of the genotype related to a very severe syndrome. We call it a PSS. Porcine stress syndrome. So what this means, there are some of the genotypes, those hog or swine or pig, they are less tolerant to stress, which means any stress will cause the severe releasing of the calcium from the SR. They cannot control very well. So we want to explain that to you a little bit more. There are kind of two examples. So here is a number one example. We don't know the type. There is no specific breed name for that, but we have a certain genotype which has a problem. Is this is go back to we talk about here, sarcomere, and we also talk about the calcium release from SR. Now, of course, there's absorption, release and absorption from SR. The calcium release absorption from SR is regulated by two proteins. What are the two proteins? One of them is YRY. Another one is DHPR. That's an acronym. And the full name, the first one, is we call it, I want to make sure the spelling is correct. The first one is ryanodine. And the second one is dehydroxypapain. pyridine. So those are the two proteins. Okay, these are two proteins. Regulated the calcium release and absorption. Now, DHPR, this is a censoring of voltage change at cell membrane system. So you know that once you have a stress signal there, this protein will be censoring that. Now, ryanodine, the name coming from a research which is showing this specific protein is affinity, which means attaching to a toxic plant. And the toxic plant is ryanodine. Now, therefore, we name the protein as RYR. There are three types: type 1, type 2, and type 3. So type 1 is widely existing in skeleton muscle, like legs, like the carcasses. Type 2 is widely existing in cardiac muscle and the brain. So type 3 is all other tissue. So here basically is a type 1. Now since it is a protein is composed by amino acids. And this amino acids is very long sequencing. So what happened is, the sequencing is very long. Some of the swine, if they have PSS, porcine stress syndrome, at 1,843 residue of the amino acid sequence of RYR has one genome base changed, is T replaced with R. T replaced with C. Only one genome change. So what is T? That is thymine. So we can go back to review what the thymine looks like. Okay, 6 carbonyl group right here. Then you have NH. Then you have NH. Double bonds, CH3H. Now what's a cytosine looks like? So we are going to talk about chemistry. Cytosine looks like very similar, lots of the structure with thymine, but there is some difference. Okay, what's the difference here? They do not have a methyl group, they have H, and here they have NH2. Here are the same, they still have O, and here is NH, and here is NH. So that's cytosine. And then we talk about, this is DNA, then goes to mRNA, that's transcription, and finally become an amino acid sequence, later on become a protein. Once you have here is T replaced with C, the whole thing down here causes change. As long as we talk about the position, 3 codon, messaging, is that right? If it happens on the last one, maybe okay, because Wolverine infects, if this single unit of the genome base is happened at the middle, or the first one, will cause a problem, which is we call it a mutation. Now, why the mutation will happen? The reason is The DNA going through transcription and translation, there are no proofreading. All we can say is there is no fixing mechanism behind it. Therefore, at the end, what will change is the amino acid sequence will change. So originally, it is a cysteine. And then it becomes what? Becomes an arginine. That is cause the problem. Once this mutation happened is, the swine or the pig or the hog has pulsing stress syndrome. It looks like this. The calcium will dramatically release from SR and cause one syndrome, malignant hyperthermia. Okay, so that's one of the reasons. This tells you some of the swine breed or the species, we don't know which one, just generally say will have PSS, less tolerant to the stress. The reason is mutation at 1843 residue of the amino acid sequence of RYR. Now, of course, it is type 1 RYR. The only single gene-based change is thymine become a cytosine. They don't have a proofreading capability, so amino acid from cysteine becomes arginine, then makes them more stressful to the cannot handle the stress easily, and let the calcium dramatically released from the SR. Okay, so that's one of the reasons will cause PSU. The second example is there is a special gene or special breed we already know is a Nepo gene. So the Nepo gene, they are had we call it NAL plus and also NAL negative. Those genetically we call it allele. So what happened is they're using RNT. Some we using RN we call it. Okay. So this is RN plus and RN negative. That is allele. So for RN plus breed, they have normal amount of glycogen. However, the allele RN negative, they have huge amount of glycogen in the liver. So why they cause a difference like that? So generated glycogen is regulated by a protein called AMP activator protein synthesis. This is a protein, it's an enzyme. The enzyme has lots of the sequence, you know that. They also have a primary, secondary, tertiary, and a quaternary structure. At their quaternary structure, they have a gamma subunit. The gamma subunit, there are 200 residue. At the gamma subunit have one of the gene base mutated, then causing should be a glutamine mutated to become arginine. Once this sequencing changes, they cannot very functional work by this synthesis. This is controlled glycogen at appropriate amount. If this enzyme is dysfunctional, what happens? They will create a huge amount of the glycogen. Okay, with a huge amount of the glycogen generated in the body, during the post-mortem rigor mortis, we just mentioned about, going through glycolysis. If the glycogen amount is very, very high, what will happen? The glycolysis will happen dramatically. Then end up with huge amount of the acid will generate. So this will generate huge amount of acid during post-mortem glycolysis. Okay, when the acid generated, what will happen? Of course, pH decreased below 6.0 rapidly or dramatically. And then, you don't forget about this guy, what will happen? This goes very close to 5.0. That's water holding capacity at the lowest one. They will cause what? So water comes out. Huge amount of the water going to come out on the surface. They cannot the reflection of the light too much, so it looks like it's pale. Okay? So now why it will cause soft? Because calcium is dramatically released from the sarcolemma reticulum, and then all these proteins surrounding the Z line will be dramatically hydrolyzed. We want a little bit of amount there, although we don't want a tough muscle. If they're all gone, the muscle tissue obviously will become very soft. So these are the two things happen on the PSC a lot, which is the gene-based, which is breeding, the genetics problem caused by that. Okay, so that's a PSC POC. Okay, how about the beef? Beef related to the tenderization, the post-mortem. We have another is DFD beef. So what is a DFD? That stands for dark, firm, and dry. Now, it's different from the genetic base caused PSE. DFD basically is weather. It happens usually in the winter, in the moisty, humidity, or we say damp weather. So what's the problem with DFD? They are too little amount of storage glycogen. So we want a glycogen in the appropriate amount. If the too little glycogen, what happened at the post-mortem? This pH way too high from 5.5. So ideally it should be 5.5. It's around here. It's like more than 6.0, some point 6.5 even. Then cause a problem. What's the problem? Absorbed the water too much. The water holding capacity is too long. So they will be absorb the light. So no much light reflection. And with this pH is away from the IP value, will cause slight deassociate of myoglobin. Myoglobin is a colloid structure, has 4 subunits. They could have a slight dissociation of the subunits. So make the color is not like that red. And also they could be cause a little bit of separation of other beef tissue, muscle tissues. So that's why they have a DFD beef. Okay, but that's a seasoning cost. So this is something we introduced to you. Now, other thing we want to mention related to the tenderization. We have another topic we want to mention is connective tissue. Connective tissue. So we talk about all these. We talk about the muscle structure. We talk about avoid cold shortening, PSE, DFD. This is basically is like a physical and a chemical reason behind it. But we also notice that relatively new in the recent 20 years, there's a new theory talk about is the intramuscular fat should be in the appropriate amount, because the intramuscular fat could squeeze or even break down a little bit of connective tissue. This also will contribute tenderness. So very briefly, intramuscular fat, how we measure that? In the meniscus area, we have a marbling score. So you know could be the beef could be as a primer, as a selective, as a labeled as choice. This is a whole other discipline of meat science called meat judging. So you see lots of the university in the Middle West, let's say Colorado State University, Kansas State, University of Nebraska, they all have in the Texas A&M, they all have a very good meat judging team. They are judging for the marbling score. Okay, so that's a huge topic. And another topic, the judging could be made by the human being, by students, have different judging team. They also could be using using AI technology, using a machinery or scanning or computer system to judge that. So that's intramuscular fat. We're not going to talk too much here. Okay, but we want to talk a little bit about the connective tissue. Connective tissue have a very important components. It's called collagen. So what's a collagen looks like? Collagen underneath X-ray diffraction, it is, if we're using X-ray diffraction methods, you will see the collagen, it is triple helix. It is triple alpha helix. And the most of the collagen in the connective tissue, it is basically, we call it a type 1 collagen. So it's composed with 2 alpha 1 and 1 alpha 2. Okay, so very briefly we want to talk. So collagen, when they do the assembly, there are basically 3 steps. We call it a pre-collagen assembly. The second step is called self-assembly. And the last one is we call it a progressive cross-link formation. And the cross-link formation is rely on covalent bonds. So that's why the collagen usually is very strong. So if you want to draw a picture, it looks like that. Originally it looks like this. So you have another one like here. So how they connected? Use these double bonds, single bonds. And then here you will see like NH2, like these like carboxy group, but not H. H is an aldehyde. They'll have these group will be generated. And if we want using a more detailed tools could see the structure is basically has N terminal and the C terminal, so amino terminal, carboxy terminal, and the center. The center most likely is triple helix. N terminal at the end is non-triple helix. C terminal also non-triple helix. And the center is the dominant structure. This usually more than 95%. Okay, now what else we are interested in? So the collagen has been generated. We are interested about its sequencing, its amino acid sequencing. That has been done a lot of the research. And we find the sequencing is very interesting. Is glycine, proline, but they have a very special special amino acids. Is hydroxyproline, and then glycine again, and had a hydroxylysine. Okay, so what is a hydroxyproline looks like? So this is a hydroxyproline. So we know what a proline looks like. NH2, CHCOOH. Then I said we have to draw the whole thing. So we draw CH2, CH2, and CH2 because it's a circle. Here they add OH base. That's hydroxyproline. Okay, what is hydroxylysine? We haven't talked lysine for a while. Lysine is, we call it epsilon amino acids because it has a very, very long chain, CH2. It's like 4. Okay, go ahead, NH3 plus. Here, they're adding an OH. So that's a hydroxylysine. That's an amino acid sequence. The next one we want to talk. So for the collagen, we are talking about these pre-harvest. It's a process. If we have beef products, if we go to do cooking, what will happen? It will shrink. So if we would do the cooking at around 60 to 70 degrees Celsius, simply you will see it shrink. This we call it a TS temperature, shrink temperature. Where, the collagen will become a little bit short. Okay. We don't like it. It's if we cooked beef 60 to to 70 degrees Celsius. It's actually short, but it's very tough. So what we have to do, we need to increase the temperature. So we are cooking at more than 80 degrees Celsius using boiling methods. Then all of a sudden, you find that the beef is become very soft. Why? The reason is, at this moment, it's no longer called collagen. Collagen becomes gelatin. And this process we call solid undissolvable protein become kind of like a melted, not really, become a soft dissolved protein. So become a gelatin. Now, if we talk about the gelatin, we're going to go here. There are two different types of the gelatin. Two different types of the categories. One of the categories what we can do is using molecular weight. So using molecular weight, the gelatin could become alpha, beta, and gamma. The molecular range is 80 to 125 K, that's alpha. If the molecular weight is 160 to 250 K, that's beta type gelatin. If it's 240 to 375 K, that's a huge molecular weight, it's a gamma gelatin. That's based on the molecular weight. We also could be based on the treatment. We can categorize type 1 and type 2. So type 1 gelatin, we're using acid treatment.